Alright, hello everybody. This video is going over the AP Chemistry Quest for Unit 3, Lessons 7 through 13. Number 1 says, which sample demonstrates particles arranged in a regular geometric pattern? Remember, we've gone over in Unit 3 a lot about the structure of different compounds and how they look in different states of matter. We know that when you have a gas or a liquid, those molecules can move past one another so they can flow in a sense, which is why gases can take the shape of any container, and same as liquids. However, when you get into solids, those molecules are going to be arranged in a geometric pattern in which that substance does not fit a certain container. So if you had, for example, an ice cube and you put it in a glass, that ice cube is not going to change any shape while it's still an ice cube. So that's just one very simple explanation, but the answer to this would be B, because you have CO2 in solid form. Now the reason D is not the answer is because aqueous means dissolved in water. When you dissolve something in water, that means that that molecule is now going to be flowing in a sense through all of those water molecules. So it's not going to be in a geometric pattern any longer. So the answer to number 1 would be B. Number 2 asks, which temperature does a water sample have the highest average kinetic energy? So we know that average kinetic energy is directly related to temperature. So as we increase temperature, we're going to increase our average kinetic energy. So the first thing I would personally do is just get all of my options to the same unit. In this case, since we have more Kelvin, I'm going to convert A and B to Kelvin. So now that all of my answer choices are in the same unit of Kelvin, I can see which one has the highest amount of temperature, which gives me the highest average kinetic energy. So in this case, the answer would also be B. All right, number 3 asks us which is inconsistent with the kinetic molecular theory. If you look at the bottom of the screen here, I just posted the 5 assumptions with kinetic molecular theory. You can see on the 4th one down here, it says there are no forces of attraction or repulsion between gas particles. If you look at A, it says gas molecules have forces of attraction for each other. That would be the answer, because in our kinetic molecular theory, we know that with gas particles, there are going to be no forces of attraction because they are moving so fast and at such rapid motion that they are not going to experience those forces of attraction between each other. So A would be the answer for this question. An ideal gas law at STP occupies 22.4 liters. If the pressure on the gas is increased to 1000 torr and the temperature of the gas is reduced to 250 Kelvin, what can be said about the gas? So if you look to the right of the screen here, I posted all of the things from your AP Chemistry reference sheet that you can use for this specific question. So if you look at the small table I wrote on the side of the screen there, you can see that we were given 3 initial values. It told us that our ideal gas was at STP at 22.4 liters. So we know that it was 22.4 liters. It had a standard pressure at 760 torr, and it had a standard temperature at 273.15. Again, those are all given to you on the reference sheet. You don't have to memorize those. And then it gave us the final pressure, which is 1000 torr, and the final temperature, which is 250 Kelvin. So we know we're going to be solving here for the final volume. So from our ideal gas law, which is given to us on our reference sheet, we can form the equation that has to do with volume, pressure, and temperature. So we will be using P1V1 over T1 equals P2V2 over T2, and we are going to be solving for our final volume, or V2, which is going to give us P1 V1 T2 over T1 P2. So let's plug in all of those values. So here are all of our values written out in the equation. We are going to do 760 times 22.4 times 250 divided by 273.15 and divided by 1,000. So that's going to give us 15.58 liters, and we know it's liters because our Kelvin cancel out and our torr cancel out. So our final volume is 15.58 liters. So we know we went from 224 liters, 22.4 liters to 15.58 liters, which means our volume of the gas decreased. So the answer for number 4 would be C. Number 5 says a mixture of gases exists in a sealed container with the following percentages. Helium has 40%, neon 50%, and argon 10%. If the total pressure of the gases is 1100 torr, then which of the following is true about these gases? So if I were doing this question, I would immediately go ahead and multiply our total pressure by the relative abundance of each element, just so I knew exactly how much pressure each element had, just to make my answer choices easier to get rid of or accept if it's the right answer. So if I have helium, I know helium is 40% of 1100, so that's going to give me 440 torr. For neon, it is 50% of 1100, so that's going to be 550 torr. And for argon, that's going to be 10%, so that's going to be 110 torr. So now I can go ahead and look at my answer choices, and I see these ones that have the actual amount of pressure. This one says the partial pressure of neon gas is 550. That is correct. So C is the right option, and I got it just from doing that simple math. Number 6 says, which of the following explains why the melting point of sodium chloride is lower than the melting point of calcium fluoride? So we went over this more towards the beginning of Unit 3, but it kind of applies to the entire unit. We know that from Coulomb's law, the first thing that's going to affect the melting point or the boiling point of a substance is going to be the charge within an ionic compound. So as you increase the charge, you're going to increase the boiling point or the melting point. So in this case, calcium fluoride, the calcium has a positive 2 charge. And then in sodium chloride, they both have a positive 1, negative 1 charge. So just due to the charge of the calcium, that is going to increase the melting point, which is why sodium chloride has a lower melting point than calcium fluoride. So the answer here is only 3. The charge on the sodium ion is less than the charge on the calcium ion, which means the answer is C. Number 7, which of the following best explains why 1-butanol has a higher surface tension than its isomer diethyl ether? So if you look at the two substances, butanol or 1-butanol has a OH compound on the end of it. Remember that OH on the end of a molecule is going to participate in hydrogen bonding, which means it's going to attract to water more, which is why it's going to have a higher surface tension. So the answer to this is due to the hydrogen bonding in the 1-butanol, which is the top substance. So the answer for this one would be E. Number 8, what is the mass of sodium chloride required to make 25 milliliters of a 3.5 molar solution? So we know that we were trying to find the mass. So with molarity, you should know at this point that molarity is moles over liters. This is given to you on your formula sheet for AP Chem. You could have looked at that if you needed help. So if we're trying to find mass of sodium chloride, we're going to first solve for moles and then convert to mass. So in order to solve for moles, that's going to be molarity times volume. So our molarity is 3.5 and our volume in liters is going to be 0.025 liters. So if we do 3.5 times 0.025, that's going to give us a 0.0875 moles of NaCl. Now that we have that many moles of NaCl, we can go ahead and convert it into grams. So we know in 1 mole of NaCl, it gave us the molar mass, 58.44 grams. So we can go ahead and multiply that by 58.44, and that's going to give us 5.11 grams of NaCl, which is A on number 8. Number 9 says, which of the following substances is most soluble in water? Remember, for solubility in water, we're looking for a few things. If everything is nonpolar and you don't have any dipole-dipole interactions and you don't have any hydrogen bonding, then you're looking at London dispersion forces, or number of electrons to increase polarizability. However, we have a substance in these options that has hydrogen bonding. Since hydrogen bonding is going to be the strongest intermolecular force for bonding, it's going to increase the solubility in water, meaning that this OH here is going to want to form hydrogen bonds with water, so it's going to be the most soluble when put into water. So D would be your answer, simply because of those hydrogen bonds from the O and the H. All right, number 10 says, which type of radiation is associated with electrons transitioning between energy levels? We know from our 3.11 work, we talked about electrons transitioning starting in the UV radiation and going into the visible radiation. That is both on the very beginning slide of the unit and also a few times in our booklet work. So that's something that you do need to know. So please add that to your memorization list if you do not know that already. Number 11 is a dilution equation. It's asking us what amount of distilled water is added to the dilute to dilute the solution. So when we are solving for our volume for the dilution, we need to remember that that is the total volume at the end. So we need to subtract the initial volume in order to figure out how much was added. So if we look at our dilution equation, which is something you do have to memorize, we're solving for the amount of water that was added to the dilution. So we're solving for V2. So if we're solving for V2, that's going to be M1 V1 over M2. M1 is 0.55 molar. V1 is 125 milliliters. The reason I am keeping that in milliliters is because all of our answers are in milliliters. And then our final molarity is 0.35 molar. So our molar units cancel out. If I multiply 0.55 times 125 and then divide it by 0.35, I end up getting 196 milliliters. Remember, this is the total volume for that diluted solution. Oof, I spelled volume wrong. So if that's a total volume, we need to figure out how much was added. So we take the original and subtract it from our 196, and that's going to give us 71 milliliters. Sorry, I had to fix this. It was driving me nuts. Number 12, what is the danger of heating a rigid container of gas? So heating anything that is tightly contained in a container, as you increase the heat of something, you're going to increase the average kinetic energy. Basically, what can happen is it's going to explode. So if you are heating a gas that is in a closed container that can't escape, eventually it will explode. So the answer with this would be A. 13, what is the concentration of chloride ions in a 1 liter solution that contains 55 grams of magnesium chloride? So here we're looking at concentration, so we're looking at molarity. So in this question, we are given the grams and liters. We know that molarity is moles over liters. So we already have our liters, which is 1. So we need to figure out our moles. So we already have grams. So in order to get from grams into moles, I'm going to be dividing by the molar mass because I know in 1 mole of MgCl2, I have 95.21 grams of MgCl2. So by doing that, I get the number of moles. So 55 divided by 95.21. That's going to give me 0.578 moles of MgCl2. So that's going to go up here, 0.578. So divided by 1, it's going to be the same thing, and that's going to give you my concentration. But now that I have my concentration, please note that it's asking the concentration of the chloride ions. In magnesium chloride, I have 2 chlorines. So I would take my 0.578 and I would multiply it by 2 because I have 2 chlorines in that specific compound. So that would give me 1.16 molarity as my final answer, or B. 14, what is the wavelength of a photon that has an energy of 1.55 times 10 to the negative 19th joules? So if you look on the right side of the screen, that is all of your information needed for this question. That is from your AP formula sheet. So if you look at the question, it's asking for wavelength, which is here, and you are given the energy. So if we are looking for wavelength, we know that the wavelength equation is going to be C over V, which is frequency, and V is going to be equal to E over H. So if V is equal to E over H, then we know then we can plug that into the denominator of our formula. So since V is in the denominator, then our E and H will be switched. So it will end up looking like wavelength equals CH over E. So now I have our speed of light, which is 2.998 times 10 to the 8th. And then I have Planck's constant, which is 6.626 times 10 to the negative 34th. And then I am dividing it by our energy, which is 1.55 times 10 to the negative 19th. So if I look at the top first, let's just focus on our non-exponents. We have 2.998 times 6.626 divided by 1.55. That's going to give me 12.8, which if you didn't want to deal with all of the exponents, you can look that it either has to be 12.8 without exponents, which is not going to happen, or this is going to move and it's going to be 1.28. There's only 1.28 on this question. So technically the answer would be A without having to do all of that exponent work. However, if you wanted to, you're first going to add your exponents on the top. So we're going to have 8 plus negative 34. So if we have negative 34 plus 8, that's going to give us negative 26 over negative 19. So if we bring that negative 19 up, it's going to add 19 to our negative 26, which is going to give us 10 to the negative 7. So if I have 12.8 times 10 to the negative 7, I have to move this decimal point over 1, which adds 1 to this. It would give me to my final answer of 1.28 times 10 to the negative 6. Again, you technically didn't have to do all of that because there was only one option for 1.28, so you could just select that without having to do all of that work. Copper sulfate creates an extraordinarily blue solution in water. Which of the following experimental techniques could a scientist use to determine the concentration of copper sulfate based on absorbance? So we've been learning about spectrophotometers for lesson 13 in unit 3. And remember, it talks a lot about color and wavelength and how when you put in a solution that's a certain color, you're going to shine a light that is opposite on the color wheel in order to show those specific absorption levels of light. So when we're talking about photospectroscopy or spectrophotometry, it kind of goes back and forth with the name. You are talking about solutions that have a wavelength of color that is needed. So when we're talking about copper sulfate that has a very strong blue color, that is just a hint right there that you're going to be using spectrophotometry or spectroscopy with wavelengths. All right, so let's move on into our FRQ section. It states a student is instructed to determine the concentration of a solution of CoCl2 based on absorption of light. The student is provided with a 0.1 molar solution of CoCl2 in which to prepare standard solutions with concentrations of 0.02 molar, 0.04 molar, 0.06 molar, and 0.08 molar. So A says to describe the procedure for diluting the 0.1 molar solution to a concentration of 0.02 molar using distilled water, a 100 milliliter volumetric flask, and a pipette or a burette. So the first step is going to be solving for how much water we need to add to the solution in order to dilute it to a 0.02 molar. So we know we have our initial concentration. So if we're doing M1 V1 equals M2 V2, we know our initial concentration is 0.1 molar. So if we're solving for V1, that's going to be M2 V2 over M1. So we already know M1, so M1 is 0.1 molar. And we have the concentration we're trying to get to, which is 0.02 molar. And it doesn't technically give you the amount of volume you're ending up with. However, it's telling you that you have a 100 milliliter volumetric flask. Now we know with a volumetric flask, there is only one measurement on that volumetric flask. So in order to complete or conduct the experiment, when you're measuring this dilution out, you have to stop at that 100 milliliter mark. So we know that when we are creating this dilution, we know we're going to end up with 100 milliliters of total solution. So that is going to be our V2 with 100 milliliters. So now that we have this, we can solve for the initial volume of our 0.1 molar solution. So when we do 0.02 times 100 divided by 0.1, we get 20 milliliters. So now we know how much to add into our volumetric flask in order to get the correct amount of concentration for the new solution. So let's go ahead and make our procedure. It can be kind of short as long as it hits the 2 steps that I will be writing on this FRQ. If you did more steps than that and you are more specific, that's not going to take any points off of your question. So the first step that is required is going to be to pipette 20 milliliters, which is what we just found, of 0.1 molar CoCl2 into the 100 milliliter volumetric flask. Then your next step is going to be add your H2O or your distilled water until it reaches the 100 milliliter mark. Then you would write to stopper the flask and mix. So this is the bare minimum of the procedure that you would need. This 20 milliliter piece was important to actually write down the procedure because you needed to know how much to add of that 0.1 molar CoCl2 into the flask. So that was a key component, was solving for this 20 milliliters of CoCl2. It then says the student takes the 0.1 molar solution and determines the percent transmittance and the absorbance at various wavelengths. The two graphs below represent the data. So B says identify the optimum wavelength for analysis. So when you see this percent transmittance and the absorbance, you're going to be looking at the two peaks, the bottom peak for the transmittance and the top peak for the absorbance. So if you look at the two peaks, they are both at 510 nanometers. So that is going to be our answer for this question is 510 nanometers. Again, this is just reading a graph. If you put between 490 and 520, so if you put 520 or you put 490, that would technically have been counted correct. But if you line up the peak of the transmittance and the absorbance spectrum, then you would see that it would line up both to 510 nanometers. The student measures the absorbance of the 0.02, 0.04, 0.06, 0.08, and 0.1 molar solutions. The data is plotted on the graph below. C asks the absorbance of the unknown solution is 0.275. What is the concentration of the solution? So this is a basic reading of a graph. So if you look at the absorbance, this would be 0.25. So if it's saying 0.275, we'd be right about here, which means we are hitting down almost at the half mark there. So it would give us a 0.05 concentration. Basic reading of a graph on that one. D says Beer's law is an expression that includes three factors that determine the amount of light that passes through a solution. Identify two of these factors. So this was technically a give you question from AP Chem. It asked you to identify two factors of Beer's law. Well, it gives you Beer's law on your formula sheet. So as long as you know that A equals EBC is Beer's law, then you are golden. Because if you look at the right side of your formula sheet, it actually tells you all of the components of that law. So as long as you knew how to find it, you could answer this one question. So it says you only had to identify two of these vectors. So you could have chosen absorbance, molar absorptivity, path length, or concentration, and you would have gotten those points. E says the student handles the sample container that holds the unknown solution and leaves fingerprints in the path of the light beam. How will this affect the calculated concentration of the unknown? So we know that the presence of fingerprints will absorb light. So since less light will reach the detector, the solution will have a higher absorbance and will report a higher concentration. So if you wrote any component of that answer, then you would have gotten points for this question. And then the last part of this quest was, why is this method of determining the concentration of CoCl2 solution appropriate, whereas using the same method for measuring the concentration of NaCl solution would not be appropriate? So remember, with this spectrophotometry, we are looking at colored solutions and how they absorb light. So NaCl is not colored. When you dissolve NaCl into water, it's going to be clear. So when you put it into a spectrophotometer, it's not going to work. It's not going to show any absorbance because it's clear and the light beam is going to go straight through. I hope this helped. If you need any more help on this unit, please let me know and I'm happy to help you at any time. Have a great day.